now focusing a lot on kind of grasp generation for unknown objects and using a lot of the techniques that come from the computer vision community. And then the second talk will be given by Nathan Radcliffe, and he's been a long-time collaborator of us. He got his PhD at CMU working with Drew Bagnell at the time, working on learning for path planning and trajectory optimization. He was one of the first people working on inverse optimal control techniques for learning from demonstration. He then moved on to TTI, right? And after that, Max Planck, and then finally came actually back to Seattle, where he started a robotics startup company doing manipulation, where we had close collaborations already here with the University of Washington. And when I started the NVIDIA lab, he was the first person to kind of join that lab, and he'll talk about some of his work for manipulator control and planning. So,
all right. Hello, everyone. As Dieter mentioned, I'm going to talk about our recent work on grasping unknown objects, which is called 6DoF GraspNet. This is a joint work with Clemens, Eppner, and Dieter. So if you think about it, most of the robot-object interactions involves the robot to be able to grasp the object of interest. And we want to be able to grasp any object without knowing its 3D model so that we can scale it to large set of objects. But grasping is challenging. First of all, the space of 6DoF grasps is huge because each grasp is represented by a 3D rotation and 3D translation. And majority of the grasps within this space are going to fail to grasp the object of to grasp any object. And basically, the success of the grasp depends on many different factors, such as physical properties of the object, like object mass, frictions, and also the shape of the gripper. So grasping is a well-studied problem in robotics, and I'm going to go over the recent works on grasping unknown objects. So the first one is from Google, that they used multiple robots to train a Q-learning policy to basically come up with a set of optimal action to grasp the object of interest. And the actions, they assume that they know the z coordinate of the table, the depth of the table, and the actions were only on x, y, and orientation of the gripper. And because the grasps were kind of constrained with 3 degrees of freedom, the effective workspace of the method was more limited. And during inference time, they use cross-entropy method to basically run the inference and come up with the actions to grasp the object. DexNet tackled this problem in a supervised way. So they generated and evaluated lots of grasps using simulator, and basically learn a classifier that assigns a score to each of the grasp poses, and they define the grasp by xy pixel coordinate of the center of the grasp and also the orientation, which again leads to limited workspace of the method. So the state of the art on 6DoF grasping was grasp pose detection, and they tackled this problem that they took the point cloud of the scene and use geometric heuristics to sample a set of grasps, and then they had this classifier that scores each of these grasps. And the way they sampled the grasp was that you basically want to sample poses where you have at least certain number of points from the object in between the fingers. And here, for the 6DoF GraspNet, we are also working on generating 6 degree of freedom grasps, and we are using point clouds as input, and we also learn how to sample grasps from the point cloud of the object. So basically, we are we are looking for this generic grass generator that can be used for different tasks. For example, assume you want to just grasp the empty mug on the left. So, yeah, it's perfectly fine to for the robot to grasp the object from anywhere. But if the mug is full, you don't want the robot to touch the content of the mug. And for example, imagine you want to pick up this mug and put it in a dishwasher. So you want the robot to grasp it in such a way that enables it to put it in the dishwasher properly. So we want to have this 6-off GrassNet as like a generic framework that can be shared between all of these, all of the different tasks. And instead of learning a separate policy for each of these situations, we want the different tasks just to choose grass from the ones that are generated using 6-off GrassNet. So the overview of our method is like this. So we start with an RGBD image of an object. In addition, we also assume that the object is segmented, so we know which pixel belongs to the object. And we back project it to 3D to get the point cloud of the object. And the first component of the system, our method is the grass sampler, which takes the point cloud of the object and generates different set of grasps. But not all of these grasps are going to be successful, so we need a way to evaluate the potential of each grasp. So the second module is the grasp evaluator, which assigns a score to each of these generated grasps. And we also want to be able to make some local adjustment to improve the quality of this grasp. So we have this third step, which iteratively makes local adjustment to improve the quality of the grasps. So first, we are going to talk about the grass sampler. So the grass sampler is basically a conditional variational autoencoder that has an encoder and a decoder. The encoder basically takes the point cloud of the object and a random grasp and map it to a value in a latent space. And during the training, we want to make sure that this latent space is similar to a prior distribution. And to make things simple, we just assumed a Gaussian prior. And the decoder part basically takes this point cloud and the value and the sample value from this latent space and reconstructs the input grasp. And basically during inference, we remove the encoder and we just sample from the Gaussian distribution, because during the training we try to make sure that the generated samples are as close as possible to the Gaussian distribution. And this latent space has is kind of structured, because if it doesn't have any structure, then there is no way for the decoder to reconstruct the grasps. So here I'm showing different grasps based on the changes in the latent space, latent value. So this is an example for a 2-dimensional latent space, and in each example I only change one of the latent dimensions. And for example, on the top left, you can see that the change in the latent results in switching between grass from the back of the bowl to the grass from the front. For the same scene, if I change the other dimension, it is kind of translates into changing elevation for the grasps. And for the lower left, it is like generating different set of grasps for the handle, and on the right, on the lower right, it's just giving different grasps for the box. And note that none of these objects were used during training. So these are all unknown objects.
Quick question. It's the first time I'm seeing these animations.
Yeah.
On the lower left,
Yes.
it seems like if you would sample from that, and the area of the Gaussian you're kind of putting your sample, getting your samples from, that it would actually be very unlikely to generate these, or?
These are all from -2 sigma to 2 sigma, so it is not.
Also 2 sigma.
Yeah,
Okay,
yeah, yeah. Good.
What determines whether a particular grasp goes in the middle of the Gaussian or the outside of the Gaussian? Or what's the, what determines the dimensions or variables constituting the latent space?
Oh, so we tried different latent space sizes, and I'm going to talk about it in the next slides. But empirically, we realized that latent size 2 was giving good performance.
But it's also learning the latent space, right?
Yes.
Master distribution.
Yeah.
But I think just for
I
clarification.
guess aren't there like an infinity possible two-dimensional latent spaces that you could use? Or a very large number anyway? Or at least 6 choose 2,
So
Choose, what do you mean again?
Well, I mean, these approximate sort of pitch and yaw, right?
Yeah,
Roughly,
yeah.
very roughly. So that would be a 6-dimensional pose of the gripper, choosing 2 of the dimensions. I guess you're going to explain this more, so I'll just listen.
And I think just as the main point is that the graph space is 6D, right? But the trick is to choose a latent space that is smaller than 6D, so that it has to learn that inherent structure. And the way these lines he's sampling from are chosen here is just for visualization. Later, you just sample from a Gaussian, and you get a variety of different graphs that you can then choose from.
Just another quick question about the parameterization of the grasps. Is it just the end effector pose that you're parameterizing
yes,
here?
end effector pose. Yeah.
So the width of the gripper itself is fixed?
It's fixed, yeah. Yeah. So you basically learn a model for each gripper. Yeah. Any other questions? Okay. So for the second module was the grasp evaluator that we basically assign a score for the success of each grasp. So what we realized from our experiments is that the representation of the data really matters for the evaluator. So what we did was to represent the grasps with a set of points on the gripper and make this unified point cloud of the object and the gripper, and having this auxiliary binary feature that basically indicates whether each point belongs to the object or to the gripper. And so that is the input to the network, and we want to basically classify the grasp as successful or failure. And the next step the next stage is to find a local transformation that kind of tries to improve the quality of the grasps. So the good thing is that we can look at evaluator as a differentiable function that takes the grasp transformation and the object point cloud and gives us the success of the grasp. So if we want to improve the quality of the grasp, we can compute the gradient of success with respect to the grasp transformation and basically move into that direction. So here these two images showing the result of different refinement steps, and you can also see the score that the network assigns to each of these graphs. So in the beginning, they start with some of the graphs will start in collision with the object, but at the end of refinement, they are getting better and better, and the score is also improving.
Can you back to the former slides, the animation? Can you spend some time explaining the different axis meanings of the?
So this one is a 2D dimensional latent space, and
So. What's the meaning of each axis?
So we don't specifically put any loss or any constraint to have like a meaningful concept for each axis. During the training, the network basically learns to assign the space of the grass to a structure, and in order for the decoder to be able to reconstruct these graphs. So basically what the network sees in the training is like a bunch of random graphs for the encoder, and the decoder has to reconstruct the input grasp, right? So if we go back to here, so what is being reconstructed here should be as similar as possible to the input grasp, right? And this latent space, as Dieter also mentioned, has lower dimension than the grasp than the grasp representation. So in order to be able to reconstruct this latent space plus the point cloud of the object has to have enough structure so that the decoder can reconstruct the input grasp, right? So this is during training. But during inference, we remove the encoder and we just sample different latent values. And so there is no explicit constraint or assignment of any concept to these latent spaces.
What do you mean by reconstructing graphs?
So basically, you want to predict a quaternion and translation that matches your input grasp.
So it's like, okay, so self-reconstruction.
Yeah.
And follow-up question, so do your reconstructed graphs also have, like, it looks like here you have the mesh of the object that you're trying to grasp. Is that something that you're explicitly trying to reconstruct here?
Oh, no. This is just for the visualization. It's just the point cloud of the object, and the only thing that you reconstruct is the quaternion and translation for the grass. That's it.
I guess my follow-up question to that is, what do you do about the holes from your depth data? Like you can't see the other side of the cup. Like it looked like in the resulting graphs that you had for the other object a few slides in the future, like you are grasping in those unknown areas.
Yeah. So the network, we don't explicitly do anything for them. All we do is to render the object from a random viewpoint and sample a subset of these points randomly, and the network itself learns to interpolate kind of these missing points from the object point cloud.
So if you had perfect point clouds, then you could do a more analytical approach, right? But the key trick is the network here learns to generate graphs even from partial point clouds. That's the main point.
How do you ensure that the encoder Q is actually utilizing the point cloud X, given that your output reconstruction and the reconstruction is G?
So basically, if you choose a small dimensional latent space, the network has to use the information from the object point cloud to be able to reconstruct.
I know this tricky, if you don't know very well like autoencoders and things like that, then this is kind of magical. But the one thing, maybe if you go back to the visualization that you had, the slide, I think, yeah, this one. Also for people to know that it's important, the same point in this embedded space will generate different graphs depending on which point cloud you're associated with it. Right? So it's not that a point encodes the full 60 graphs, it just encodes somehow which kind of grasp you would use from a certain object. But maybe in the interest of time, might make sense too.
Is there any questions on the refinement? Okay, so we trained this. We trained the model on 126 different random shapes from ShapeNet datasets, and for the point clouds, we just render the objects from random viewpoints and generate point cloud for them. And for the grasps, during the training, we know the 3D model of the object, so we sample a lot of different grasps and evaluate them in the simulator. And the way we simulate is that we execute the grasp by shaking the object in different directions to make sure that it is robust enough. And then we evaluate the method on 17 unseen different objects in the real data. And the good thing about our method is that since it works with the point cloud, there is no need for domain adaptation to do the transfer from simulation to real. So from the real experiments, we realized that generating diverse set of grasps is really important. For example, if you have a method that generates few candidates for grasping the object, maybe because of the relative pose of the object with respect to the robot, most of them won't be kinematically feasible to be executed by the robot. So generating diverse set of grasps matters even just for picking up the objects regardless of any tasks. And we also did the ablation studies to see the effect of different components. And we did the ablation studies on the synthetic data, and we used two metrics for the evaluation. The first one is the success rate, which basically indicates the percentage of the grasp that succeed in the simulation. And the second one is the coverage. And coverage is similar to the recall in classification. And it basically indicates the percentage of the ground truth grasp pose that are within certain distance of any of the generated grasps. And we basically compare different variations based on the area under curve of success rate coverage plots. So the first thing that we compared was to compare the VAE sampler versus just a geometric-based sampler. So for the geometric-based sampler, what we did is as follows. So we basically sample a random point from the object point cloud, and we compute the surface normal. And along the surface normal, we go to like a random offset and random orientation along the surface normal. And so as you can see here, the variation that uses VAE has significantly larger area under curve, which shows the effectiveness of learning how to sample the grasps. And another thing to mention is that these are with the perfect depth, so there is no missing depth. So the geometric-based sampler will perform worse on the real data because you will have missing points that you won't sample any grasp on those points. So the second thing that we checked was the optimal size of the latent space. So if the latent space is too small, it doesn't have enough capacity to model all sorts of different grasps. And if it is too large, then it becomes too sparse for the inference. So what we realized that, for example, latent size 1 it does not perform well. It has a small area under curve, and latent size 2 has the highest performance from all the different latent sizes that we experimented with. And the last one shows the effect of grasp refinement. So basically, here you can see with more refinements, the performance increases. So here are some examples on the real robot. So all of the sensing is done with the onboard camera on the robot, and basically the robot takes the observation from the scene, generates grasps, and basically execute the one with the highest score in an open loop fashion. And of course, if we do like open loop execution, we will have some errors in the grasping that is mainly coming from the miscalibration between the camera and the gripper.
So did you clarify, are these new objects, test objects that are not in the training set?
Yes.
Yeah.
Yes. So, but all of the examples that I showed so far were just single object per scene, and the robot interacts with the cluttered scene. So now we want to see how we can extend this to the cluttered scene. So first, we assume that the objects are segmented, and for the object of interest, we generate all of the grasps regardless of the clutter around those objects. And then we remove the ones that are in collision with the other objects, and from the remainder of these grasps, we choose the one with the maximum score. So we put these we basically use the instance segmentation that we developed with Chris Shi, one of Dieter's students, for segmenting the objects in the scene, and the robot always tries to pick up the closest object and put it in the bin. And here we always choose the closest one to make sure that the objects are not occluded. But we have other variations that will appear soon on arXiv that can handle occlusion as well, and they can and it can also reason about the situations that you want to, for example, grasp this mug here, but it is blocked, and the model is able to basically find out which of these objects blocking the mug the most. So this object is the one that is on the way of most of the grasps, and then we switch the target to remove that blocking object, and then move back to grasping the initial target object. So yeah, so here the blocking object is removed, and now it goes back to grasping this object. Yeah, I'm almost done. Yeah. And we also have another extension of the work to object placement, where the sampler, instead of sampling different poses for grasps, it samples different stable poses, and we also have an evaluator that basically assigns a stability score to each of these poses. And in conclusion, so I talked about how to generate different set of grasps for unknown objects, and we trained the whole model with the synthetic data and tested it on real data on unseen objects. And the advantage of our method is that it can be integrated with other components as well. Like for instance segmentation, we use like a separate model. For motion planning and control, we used Nathan's RMP flow that he's going to talk about it. And for the next steps, we want to integrate the grasping into task and motion planning to be able to execute more complex tasks rather than just picking up the objects. And another direction is closed loop control. Right now, we just make a decision in the beginning and just execute. So closed loop control is another direction for us. And then we want to also move toward manipulating objects in a more confined environment, such as cabinet, where you have also lateral walls that limits the workspace of the robot. And if you have any questions, I would be happy to answer.
Maybe while we do questions, maybe Nathan can already start.
Okay.
So one of the things you talked about in the beginning was being able to pick up a cup, whether it was full or not.
Yeah.
You showed two examples of picking up a cup. One that picked it up by the handle but tilted it over,
Yeah.
and the other one that picked it up inside to outside.
Yeah.
So have you gotten it to the point where it can pick up a cup of, say, liquid without spilling it?
We haven't tried it yet. It's for the handle right now. It's kind of hit or miss. Sometimes it is able to grasp it perfectly from the handle. Sometimes it goes to this hole in the middle, and as you saw, the mug is kind of rotates.
So would that be solved by like say a three-fingered gripper maybe?
It could be, yeah. Yeah, that's a good point.
When you're optimizing for the latent code for refinement, do you use like the gradient descent or second order method?
Gradient.
Have you considered using like faster methods?
So we also have these other variations that uses Metropolis Hastings sampling, which is much faster because it only runs the forward pass. It is much faster than the gradient descent one. But at the time, we only had the gradient-based optimizers.
Sorry to revisit the autoencoder thing, but my understanding of autoencoders is that you can provide whatever input, in this case a grasp and a point cloud in, and ask it to reconstruct one out on a limited domain. What I'm unfamiliar with is the constraining of that latent domain to a probability distribution.
Mm-hmm.
Can you talk a little bit about like how that works?
So basically, you have this auxiliary loss, which is the KL divergence between all the generated latents within a batch and the normal distribution. And basically, in each batch, you try to minimize the KL divergence.
Got it.
Yeah.
Okay, thank you.
Okay. Thanks again.
Hey, I'm Nathan. I'm going to be talking about Riemannian motion policies, which includes like the type of motion generation that Arsalan was using. This is joint work by a lot of people. I didn't list them all out here, but it's Dieter, Asiv, Anchi, who's one of Byron Booth's students, Byron as well, and a number of people. So grateful for collaboration. High level is that we want to have robots interacting with people. We want to get them out of manufacturing kind of clean environments into these very unstructured spaces where you're literally working with people, around people, in spaces where people might be doing something else and stuff like that. There's a whole bunch of uncertainty, and the robot has to be fundamentally reactive. And so a lot of what I'll be talking about today is how we structure a system around that sort of requirement for reactivity. And one thing that is kind of just demonstrating the types of reactivity that we're looking at, where everything is always going to be changing. If you have a stationary robot relative to the environment, that robot is actually not stationary. So like the most stationary robot you can actually come up with is something that's always moving and adapting to the world around it. And in a sense, that means we want to represent like the belief of the environment and always be reactive to not only like changes in the environment and stuff like that, but also resolution of that belief state. So an example of that here is this is the kitchen setup that we have at the NVIDIA lab. It's a full-fledged IKEA kitchen. I think somebody, probably Dieter, talked about it last week. But we have this manipulator, this Franke manipulator, interacting with it, perception, observing what's in the space in real time. And one of the things you'll notice about this setup here is it looks pretty precise, right? So it goes and reaches for that handle, grabs it, opens this thing, reaches for the object, grabs it, and moves it over and stuff like that. But it's precise, independent of lack of precision that actually exists in kind of fundamentally in these sort of environments where you have a camera sitting off to the side and just looking on for it. But the motion generation system that we have for it is constantly reacting even to updates of the perception itself. So as perception is resolving itself, and maybe like the map estimate is improving, the system constantly reacts to that. So we get this illusion of precision, even though like this is fundamentally partially observable. So an example of that is here, where we actually show the, this is DART, one of Dieter's algorithms, dense articulated real-time tracking. Visualized on the right, and the robot in the physical reality on the left. And basically, it's just constantly getting the feedback from that at about 30 hertz and processing that within the motion generation system. And another thing to note is if we look at this again, because we're constantly reacting and because we have this constant stream of perceptual updates, we can take points on objects themselves and actually control those points. So if you watch this, it's going to try to take that point and move it up to the lip of that cabinet up there. And as it does, the object, because it's just hanging there, moves and kind of like just hangs down and bends within the grip. But because we're controlling that point, we can still be precise because we're constantly updating the motion generation. And now we can take another point. Oops. I think it just showed, maybe. and control actually the back of that to get this constant, reliable, robust behavior of getting it over the top of that lip, even though like things are changing every single time it does this. And with that sort of thing, we end up with innately reactive systems like this. This is actually the Baxter from Dieter's lab, again using DART and showing that independent of perturbations that are happening, because it's controlling points on objects themselves, it can always be reactive and robust to those things. Okay, so that's kind of the high level of where we're going. I'm going to break that down a little bit, hopefully with not too many equations and some intuition, and some more videos. But the goal is really to have naturally reactive motion generation so that we can have robots in human environments and constantly adapting to the uncertainties. Okay, so to start off with, I want to talk about a fundamental gap between planning and reality. So in most systems, we structure things into multiple levels of planning. So we might have task planning, which is like how do you sequence different tasks. We might then figure out how to get it to move between those different tasks, motion planning. We might optimize those things and incorporate more constraints and stuff like that. We might group these in various ways, in task and motion planning, global optimization, stuff like that. Maybe we can do this about maybe 10 hertz, but things are always going to be more difficult in reality. There might be somebody like me there coming and perturbing this thing. Things might be changing constantly. And so within this structure of planning, this multiple layers, which we can do at about 10 hertz, we need a foundation of reactive control. So underlying all of this, the robot has to constantly be observing the environment and changing its behavior just in reaction to what's happening immediately. And in a sense, that has to be compatible with that entire stack of planning tools. So that's really what I'm going to be talking about. That's the foundation of Riemannian motion policies here. And if we talk about reactivity, especially when it comes to like low-level control and things like that, kind of a good starting point is operational space control here, which you may or may not be familiar with, but you can kind of think of it as like the robot has a space in front of it. We've known for a long time how to get the end effector to move in straight lines in that space, how to control orientations and stuff like that, so it can explore the environment and do that reactively and things like this. This is operational space control. What we do for Riemannian motion policies is really try to generalize that notion. So instead of just looking at the operational space, this kind of three-dimensional workspace, as well as quaternion orientation, three-dimensional orientation, we generalize the spaces which we can try to control. So instead of just that workspace, we can say it can be any abstract space that we want. It just has to be linked to the configuration space, the space of joints, via some differentiable map. So an example is this right here. If this bottom thing here is the configuration, just a set of joints, we can say each point on the robot X, which is visualized on the left as well, can be a space that we might want to control. But beyond that, each one of those might also be connected to distance spaces that we might want to control. distances to obstacles in there. And beyond that, those might actually be connected to kind of like more abstract representations of how objects might be affecting geometry and stuff and things like that. Basically, like there are any number of different spaces that we might want to control. And instead of just doing operational space control within the context of a workspace, we can generalize it to this broad spectrum of control spaces. It turns out that this notion is very closely related to Riemannian geometry in the sense of if you imagine a curved space. An example would be if you have a couple obstacles and you want to go around those obstacles, you can imagine those obstacles actually literally warping the space around them so that straight lines would go around them instead of trying to go through. In a sense, like an obstacle doesn't even exist. It doesn't make sense for a straight line to go through that obstacle because it just isn't there. And so straight lines should have to warp around it. And if you imagine what would it require to warp this space, it turns out that it's equivalent really to taking that space, transforming it to a simpler Euclidean space, something more like the geometry of the workspace, and then doing everything there. And if we do that, we kind of get a direct connection to operational space control, but in these more abstract spaces, which in many cases we don't actually have to represent. But the final kind of behavior that arises if we do that sort of thing is that we end up with these nice kind of curved paths around these obstacles instead of like straight lines in the workspace. So instead of like trying to do operational space control where we have straight lines in the workspace, we end up with these nice kind of like obstacle collision avoidance paths that just kind of nicely go around obstacles. And there's some details that I don't want to go into, but basically what this amounts to is a Riemannian motion policy ends up being a policy in conjunction with a Riemannian metric with kind of the high-level connection that I just described. And in particular, this policy encodes information about the geometry of the space, telling it how to accelerate in various ways that go around it. And there's some papers that we have on this stuff where those terms that kind of tell how to incorporate that geometry end up being curvature terms that really directly come from the metric. So that's what I just said. An example of this is actually obstacle damping. So a lot of those videos that I showed before and some of those show later have really nice obstacle avoidance properties. They just kind of naturally flow around obstacles. And to get some intuition for how they do that, we can look at an example here of what you might intuitively just try to do. So if you have like 3 obstacles here, and you have a point with a velocity, that's what the arrow's indicating, we might just describe by hand a simple controller that tries to control against those obstacles. So we might look at the distances to each obstacle. Some are close, some are far away, some are kind of in the direction that it's heading, some are kind of orthogonal to the direction that it's heading. And based on those, we can give particular weights. Okay, you can kind of see that, the purple, based on like the importance. And if we just decelerate the system in those directions based on those importance, we're basically removing components of the velocity that are in the direction of obstacles. And so if you just shoot the point in that direction and start removing components of the velocity that are in the direction of obstacles that matter, it'll just kind of naturally curve around. So that's something you might kind of intuitively write down. It turns out that that sort of policy actually falls out of the metric. So if you describe the geometry of the space and use this Riemannian motion policy math and stuff like that, that sort of policy just kind of like comes out. And so that's the sort of behavior that in general, like across the entire robot when we deal with all these spaces, we get, which is nice and intuitive, and it actually works pretty well in practice. I don't know what just happened. So here's some examples in simulation. Just very simple reaching examples. The Yumi robot, there's a cylinder forest that we placed there, and just had it try to reach to these points, and here's some examples of how it's able to get there. This is entirely local. There's no planner running at all. It's just looking at the surroundings, representing things using these Riemannian motion policies, using the intuition that I just described, and just nicely finds easy natural solutions to get to those targets. And another thing we can do with it is kind of the reverse of that, which is kind of cool. Basically, if it's threaded its arm through a whole bunch of obstacles, with Riemannian motion policies, we can just retract it very easily by just using very simple heuristics of like trying to pull back to a particular configuration and stuff. Some of these are also trying to move in the backwards direction of the end effector and things, but very complicated behaviors just falling out of Riemannian motion policies plus very simple heuristics. And this, again, is the video I showed before. This is a real-world system, similar to the Baxter, that we have at the NVIDIA lab, incorporating all of this stuff. Again, it's using Dart to account for things in real time. Because we're using Riemannian motion policies as a generalization of operational space control, it's accounting for all feedback instantaneously, which is why it can adjust its behavior in real time like this. Here's another example where I've just put it into lead-through mode. I'm pushing it around. It's moving its end effectors, and all the behavior of its elbows and how it's avoiding itself and stuff like that, or how it's shaping the arm as it reaches over the top of this is entirely generated by the RMPs. And banana behaviors, because bananas should always go in drawers. There we go. Beautiful. One of the cool things about this is, like I said, it's entirely local. And there's no planner running underneath it. You can use very simple heuristics to do things that you would typically think can only be done by motion planning or something like that. So here, we have kind of this arbitrary setup of the environment. We have a depth camera on the chest of the robot. It's creating this point cloud and voxel field of that space. We use very simple heuristics to move between different configurations or different target locations of the arms. One thing I'll note with all of these videos, because we're talking about like fast reactions and motion planning and stuff like that, they're all in real time. And so that one and this one, which also incorporates elements of Dart to detect the objects, we're all running real time and just using reactive RMPs for obstacle avoidance. And one final thing, I talked about the virtues of doing everything reactive, having this low-level bedding of reactivity. But on top of that, we still always want to integrate this motion planning stack, like task and motion planning, motion optimization and stuff like that. So this is a demonstration of, on the left, we actually have a motion optimizer running, and it's actually sending RMP representations of the solutions in real time to the RMPs and integrating those together so they can get nice coordinated behavior while it's moving. On the right, it's just using pure RMPs, which are a little bit more local, and you can see that they don't coordinate quite as well. Okay, the final thing I want to talk about is some newer work that we've done, especially over the summer with some interns, including Asif. I don't know if Antti is here, but she was part of this as well, and Byron, of trying to learn these things. Because one of the issues with RMPs, like it looks great, it looks easy and stuff like that. There's a whole bunch of these things. We have a whole bunch of task spaces, a whole bunch of RMPs on those task spaces and stuff like that. Each one of these things has parameters. And I've gotten very good at tuning those parameters over the years. And so like if you're me, you can get these things to work really well. But if you're not, we want to use some of the learning from demonstration or reinforcement learning techniques to be able to learn within this structure policies that just tune themselves from data, basically. So in this example, we did human learning from demonstration. These are just some examples of the types of things which are in that field. Basically, you're trying to kinesthetically teach the robot, move them in particular paths, and try to get them to generalize from that. So that's kind of the framework that we were looking at. And the specific algorithm that we played with was taking end effector potentials and using some of the same mathematics from the Riemann motion policies to warp those potentials so that they generalize data. So if we have multiple demonstrations of how the system should behave around obstacles, for instance, we can take one of those, use any of a number of potential learning techniques. I think here's an example. The one we chose was basically just puts a whole bunch of quadratics along the trajectory, weighs those in a nice way so that we have stability guarantees and allows the system to always track that trajectory well. But we want to take that and then warp it so that it can generalize the data from multiple demonstrations. Am I out of time, actually? Like, is it? OK. I'm almost finished, so I'll wrap up quickly. But the high level is that on top of that policy, we can learn a particular Riemannian metric, which effectively stretches the space in a nice way so that we can take any arbitrary potential and warp it so that it actually generalizes the behavior well. An example of visualization of that is this here. So under here, we have 4 example trajectories. The one in red is one that's used for generating a particular potential. The initial potential is what's shown behind it. So it kind of converges to the red thing really fast and kind of ignores the other trajectories. But after learning, it actually is able to generalize the entire behavior pretty well. So now all of these integral curves kind of nicely follow the flow that's demonstrated by all the trajectories. And here's some examples of this in play. Here's Asif demonstrating how to close a drawer in a number of different ways. Basically just move I like to call it the head, down to the drawer and push it shut. And after training from all this stuff, here's some reproductions of this from different initial configurations. So it's generalizing how to actually do this behavior. And one of the cool things that we can do with this is because it's part of the RMPs, we're basically representing this learned policy as an RMP on the end effector. We can then combine it with a whole bunch of other RMPs, including optical avoidance RMPs. So here we're just taking that same learned policy, combining with optical avoidance RMPs, and it generalizes or it adapts to obstacles in its space while doing basically the same behavior of trying to shut this drawer. And that's about it. Thanks. If you have any questions. Yeah.
So for the last part, I'm wondering what are the specific parameters you have to tune for RMT and what needs to be learned? Is that because the policy sort of falls out from the metric space? So are we actually learning the metric space for a specific task?
Yeah, actually, it is. You're exactly learning the metric for it. So designing those metrics by hand can be challenging.
By designing, you mean like how far away should I avoid this obstacle?
How far away you should avoid the obstacle, but also like, should I avoid the obstacle in particular context? One thing I didn't talk about here was that the metric can be position and velocity dependent. So is it really like what profile, like when should that metric hold and when should it not, and things like that. You can design those for specific cases and tune them for particular examples, but having a tool which can learn all of that stuff is super useful. Yeah.
So I really love the elegance of it, like 80s operational space control is classical mechanics, and this is general relativity. So I really kind of dig that. And I kind of wonder though, like, what exact problems with the classical approach are solved by this? What exact are you now free of local minima or periodic cycles attractors or anything like that that people sort of criticized operational space control for features like that. So is this like demonstrably less susceptible? You're not going to introduce a new thing like event horizons or black holes or something. So
there's I think a few answers to that. One is that operational space control was originally developed around operational space and the null space. So you kind of separated those things out. And so just the simple act of like being able to combine all of these things in like multiple different tasks and have them trade off in the right way by designing metrics that give you more flexibility for what directions in the space they care about, and a specific algorithm for like propagating those back through like chains of differentiable maps. That's really useful in practice. The other one is that operational space control was actually, like you say, built on classical mechanics. And in that sense, all of it was creating virtual classical mechanical systems. But one of the things that I didn't talk about too much is that in obstacle avoidance, you really need more flexibility, because classical mechanics will effectively say that the priority of a policy is velocity independent, which in the case of like obstacle avoidance, that means that if you're going toward the obstacle, it cares as much as if you're going away from the obstacle. And so we actually had to generalize it so that the metric or priority is velocity independent. And so that was one of the papers on RMP flow that we had here. It was actually also done by an intern last year. And so those are kind of like two ways. There's a handful of other things. But yeah, it's high level. Yeah.
So some of these tasks, like banana and drawer, seem like big tasks. Like, I mean, not actually, but like fairly complex. What is like and you talked about like you still want to have planners running, but when does the task become so complex that you can't do it simply with RMPs? Some of these things really seem like they're very complicated.
Yeah. Actually, this is another part of the answer that I was going to say, but I forgot, which is operational space control is largely around potentials, just kind of pulling, and it results in local minima and stuff like that. There will be those problems, like with this, because it's inherently a local policy. But it gives us a stronger connection to general value function approximation and a context where we can look at potentials and the metrics that are associated with them as compact representations of value functions. And so getting to your question, when you have motion planners and motion optimizers, those things are creating more sophisticated value functions. And so they fit very well within the context of RMPs. And so the question is always like how sophisticated does your value function have to be? Many cases for complicated problems, you need a sophisticated value function, either learned or from planning or motion optimization. But what this is showing is that many of the problems we thought were hard, especially obstacle avoidance, are actually much easier than we thought. And so I'd say RMPs are saying that many things are actually easier than you expected, but the same fundamental problems still hold. Cool, thanks. 29.